Thanks, Ran, for inviting. This is a great pleasure to be here. So I'm going to be talking today about a certain dynamical process or dynamical system which people studied while looking at an organism called slime mold. And based on that dynamical process, certain algorithms were proposed for very central flow problems in theoretical computer science. And in today's talk, I will tell you an analysis of some of these algorithms in terms of convergence and bounds. So let's start by introducing the central character, the slime mold. I guess some of you, or probably many of you, would have seen this video, which shows how amazing this object is. If not, here it is once again. So this is a slime mold which when initially laid out on the maze uniformly first tries to connect itself, occupying the whole maze, and then as you see at 2 points A and B, certain food is supplied, and once the slime mold senses the food source, it starts to eat the food and starts reorganizing its body on the maze. And in very suspenseful music, which you might not be able to hear, can anybody tell what is going to happen? So this is, I think, not real time. Yeah. Otherwise, I wouldn't be giving much of this talk if I were to show you this in real time. But really what happens is that the dynamics of this slime mold are such that what remains of it is the shortest path in the maze that connects the two food sources. Okay? And as the scientists will very correctly demonstrate in a moment, they overlay the shortest path, and there you have it. So this organism, through its dynamics, rather mysterious dynamics.
Why wouldn't it split?
Sorry, what do you mean? Why wouldn't it split?
Why would it not disconnect itself?
It's a single-celled organism. It's a single-celled organism. Yeah. So what it really is doing is apparently trying to solve this following problem, which in our language, in graph theory, is called the shortest path problem. So here you're given a graph, let's say an undirected graph. You're given a source node S and a sink node T, and edges have some costs. And your goal is to output the minimum cost path from the node S to T. Okay, everybody here probably knows this problem. So this was the consensus that emerged after looking at these dynamics, after looking at these experiments, that the organism is really solving this problem. So then the first question that arises is, how does it do it? Okay, so towards this very nice a dynamical system was proposed by Teru Kobayashi and Nakagaki in 2007. So as you may imagine that this organism has to do with fluids. What I will explain to you here is its dynamics imagining fluids are like electrical currents. So it's really analogous, but it will be more convenient for us towards later. So I'll use this moment to introduce it as electrical currents. So the dynamics that were proposed were the following. So associated to each edge in the graph, there was a quantity, which I will denote x sub e. And at time 0, this was set to be some positive quantity. So you can imagine putting this yellow slime mold on top of every edge in the graph. So that's what it means. Now each edge, once you have these x's, could be thought of as a resistor whose resistance was the cost of the edge divided by the x value. Okay. So for it to make sense as an electrical network, we would want that this number is positive. Okay, so in our instances, we assume that the costs are positive, and also these numbers xet to be positive if all this has to make sense. once you set it up as a resistor network, you naturally compute an electrical flow, which we will use Q sub E to denote the amount of electrical flow in that edge once you have 1 unit in current at S and 1 unit out at T. Okay. Now once you have this electrical flow, the next thing, as you see the slime mold tries to readjust where its mass lies, it updates the conductances, and this is what they proposed. That the rate of change of these x variables, which are indicators of conductances of this network, change via this formula. So if you think about it qualitatively, what it says is that the larger the flow, the larger the conductance, okay, with respect to your current. So these are the dynamics that were proposed by these mathematicians or scientists. And the natural questions that concern us are whether the solution exists and whether to what and where does this process converge to. Because what we saw was a biological process. This is a purely mathematical model which is trying to understand what it is doing. So it better be the case that the solution exists and it converges to something meaningful, for us in particular to a shortest path in a graph. And this was indeed observed for several graphs by another two Japanese scientists, Miyagi and Onishi, who showed that these dynamics indeed converge to shortest path on some special class of graphs. One thing that I would like to point out here is that all these results of convergence assume that the shortest path is unique, and we will. I mean, I can talk offline how to get rid of this assumption, if someone is interested.
And what does the mode do? Does if the path is not unique?
That's a good question, actually. So I don't know. But it seems like okay. So if you look at the dynamics. If there are really two paths of equal length, I think at a molecular level, it's really difficult to construct two paths of equal length. So there must be, as you saw in that experiment, right? You know, it's not really a straight line. So all this is to be taken with a pinch of salt, I believe. But if there is a unique shortest path, then it does converge to the shortest path. If there is really an absolute tie, then it lands up in the space of the unique solution, optimal solutions, right?
Are there theories about rates at which this happens, or?
Actually, that's what we are going to study. Yes, yeah. So first to convergence. So the first real convergence proof for this was proposed by Bonifaci, Melhorn, and Verma in 2012, who showed mathematically rigorously that this indeed is the right answer for all graphs. They also considered the problem of uncapacitated, undirected min-cost flow problem, which is elder brother for shortest path. It's the following problem, that now you're given a graph, and instead of two nodes S and T, you are given a demand for each vertex. So B is a vector which measures how much demand is there at each vertex. This could be a positive number or a negative number. Okay, we assume that the total demand sums up to 0. So for the shortest path case, you had -1 at S and +1 at T. Again, there are edge costs, and the output is again to find a flow which satisfies these demands and minimizes the cost. So notice that here in the when I take into account the cost, I look at the magnitude of the flow through that edge. Okay. One constant that will keep appearing is the maximum cost. So if you want to, for this talk, just assume that this constant is just 1. So this is so they also showed that not only does the dynamics for this converge to the shortest path, almost similar dynamics converge to the solution of this uncapacitated undirected flow. Now here, the dynamical system changes only by the fact that instead of solving the electrical flow for the demand vector 1 and -1, you solve it for the demand vector B. Okay. However, going back to your question, none of these results give any indication on the convergence time of these methods, of these dynamical systems. In yet another extremely ingenious report, Ito et al. Considered a non-symmetric or a directed version of Physarum, which was aimed at solving directed graph problems. So, I mean, if you notice that till now we have been talking about undirected graphs, now we talk about directed graphs. So for given a directed graph, you want to find the directed shortest path and a directed flow. So here, the dynamics are different. Instead of looking at the conductance change not only just based on the magnitude, but they also take into account the sign of the flow through that edge. Okay, so this changes things quite a bit. So this number need not be positive, for instance. Okay, because this is an electrical flow through an edge. It could be going this way or that way. So they showed that assuming a solution exists, that the solution does indeed converge to the optimal solution. Again, assume a unique optimal. However, in this case, the fact that whether this dynamical system has a solution is not at all clear. I mean, one can write any dynamical system they want. That doesn't mean that there is a solution to it in the range that you are interested in. And the real problem here is that these x's can start becoming negative. And once they start becoming negative, the model loses its physical meaning, because we don't know what it means when resistors are negative. Okay? So why is this exciting to us? This is really exciting because it raises this possibility of solving some very fundamental graph problems by algorithms which are inspired by nature. And such algorithms have been termed natural algorithms by Bernard here. And these flow problems are particularly interesting because they're very basic. And many flow, matching and flow problems reduce to directed min cost flow via simple gadget reductions. So it would be really very nice to have an understanding of whether we can, from these dynamics, we can design algorithms. Yeah.
In the very first setting, whether you wanted to compute the shortest path in an undirected graph, is it easy to see that if there exists a unique shortest path, that's the fixed point of the dynamic?
No, it's not easy to see. Yeah, none of these things is, that's a very good question actually. It's not at all easy to see, at least from my point of view. So let's talk a little bit about efficiency. So normally, so we are still in continuous time, and what we want is that in continuous time, the solution to this dynamical system comes close to the optimal solution in time, which is polynomial in the input size. This is the traditional notion of efficiency in theoretical computer science. Unfortunately, for these dynamical systems, one can construct simple examples where the time to convergence necessarily depends polynomially on the magnitude of the input number. So what do I mean here? So look at a two-vertex graph, S and T. There are two directed edges, both going from S to T. One has length C and one has length C minus 1. Okay, so this is really something where the Physarum dynamics take a huge amount of time to figure out which one is the larger one. Okay, and you can show that the time it takes is proportional to C. Okay, so whereas if this was really an efficient dynamics, then you would expect something which depends logarithmically on C, because C is a number which is given to you in binary.
I think it is natural because this is close to having two paths with the same length.
Yes.
So it should be diverging when one is close to two paths of the same length.
Yeah, so it reaches very quickly to the, so this is really, the solution to this is really on the plane 1, 0, 0, 1. It really reaches quickly to that line, segment joining 1, 0, 1, 1. But then it takes a long amount of time to figure out where to go. So if you're just interested in approximating the value of the flow, then this example doesn't hold. But if you really want the solution out of these two.
So if you had C over 2 and C, how long would it take?
Oh, then it's pretty fast. Pretty fast, yeah. Yeah. Yeah, so you could do tricks like, adding some random noise and so on if you really want to do that, but yeah. But if you really want a rigorous mathematical result, you will not expect something which depends logarithmically on C. Okay. In fact, this question was raised in the previous work. Somehow they missed these simple examples. So in our notion of efficiency, we allow polynomial dependency on both the largest cost and the largest demand. Okay. So these are algorithms which are polynomial, and these are typically called pseudo-polynomial algorithms in theoretical computer science. So, okay, so one might argue that this is a negative thing, but actually I still take it as quite positive, because nobody is, if your real interest, let's say you're an algorithm designer and your real interest is in designing algorithms, nothing is to say that you cannot take these dynamics, play with the step size and come up with really efficient algorithms, and at the end solve the problem faster than anything that you know before. So in fact, that was my original motivation to start looking at these dynamics.
Or you don't have to solve it exactly, but
yeah,
with high proximal.
Yeah. We only talk about good enough approximation. You'll start seeing real theorems in a little bit.
To compute the flow, is that something easy?
To compute the flow?
Yes.
Yeah, we will come to that as well. So it's now known to be easy. Okay, so in past work on this, typically the researchers consider discretizations of this, where there is standard first order discretization using Euler's method, where you have a step size h, and so here many of these issues which you would face in the continuous dynamics kind of disappear, because by definition you can always have a new point to go to. It may get negative, but you still have a new point to go to. And in a very nice piece of work, Becchetti, along with some of the authors, Bonifaci, Melhorn, and others, proved that for the undirected shortest path, these dynamics, these discrete dynamics with this step size converges. And what it means is that it finds, it comes within 1 plus epsilon of the shortest path in something that goes basically like m iterations. Okay?
How do you include here the unicity of the furthest path?
Sorry?
How do you include the assumption that there is a unique furthest path?
How do I include this assumption?
Yeah, but if they are almost equal, it must take a long time also. So
Yes.
it is at the
No, but this is fine, because here you're allowing it to depend on C. So if they're
they are integers.
yeah, they're integers. Yes. Yeah. Okay, so let me just remark that this, people here probably are very familiar with this, but let me still remark that to obtain such results in the discrete world, it is not sufficient to just prove such a bound in the continuous case, because if you just, it doesn't. So you still need to prove this result in the discrete case, and it requires some clever arguments, even if you have such a result in continuous time, because the error in Euler's method grows exponentially in time. So what about the directed version? They also considered a directed shortest path problem, where again they had a natural similar dynamics. Instead of the absolute value, again the unsigned flow, or rather signed flow, and they proved that the solution is always positive. Here it is, even in the discrete case, it requires work, and it converges, and there was no bound on the convergence time. So the question that interested us was, what about the convergence time for undirected and directed flow problems? Can we prove similar results? And the answers are yes. For the undirected min cost flow problem, which is the generalization of the shortest path, we can prove essentially a similar result that was proved by Becchetti et al. So you're given a feasible instance of undirected min cost flow, and we run the discrete undirected dynamics with a step size of about 1 by n, where n is the number of vertices, and we can reach within 1 plus epsilon times the optimal in these many iterations. So this result improves the previous result in two ways. One is that it works for every min cost flow instance, and secondly, it reduces this dependence on the number of edges to the number of vertices. Here is again one notation which I will keep using again and again, which is BP, which is just the total demand of this instance.
The demand is epsilon.
No, it's the same. It's the same. It's the same epsilon cube. Yeah. So 1 epsilon comes from here, and 2 epsilon comes from the convergence number of iterations, which is low.
Start with some specific initial configuration.
Yes, yes. So I would expect this to hold for any initial configurations, but we prove these for starting where every edge has the value BP, which is the maximum, which is the total demand. Okay. And you will see in a little bit why these things are required.
Is it reasonable to take always the same step size and see?
No, it's not at all reasonable. In fact, this is why, this is what I expect to do when to get really efficient algorithms in terms of polynomial time algorithms. Yes, yeah. No, this is just very strong evidence that. Okay, so something philosophical, but if you really were to build a Physarum computer, right? There is no way for you to give the length in binary. You really think of it as a unary computer in my world, right? So this is as strong a statement that you could prove for Physarum dynamics. But if you're really interested in deriving a real algorithm from this, nobody is stopping you from changing the step size. And in fact, we know lots of tricks from analysis where different ways to pick step sizes gives you very fast convergences.
So what do you mean you combine it with solve on a comparison computer?
So I think one of you asked this question here. What about computing electrical flows? Can it be done fast? And the answer is yes. On a computer, it can be done really fast. You can compute electrical flows in time, which is really proportional to the number of edges. This is an extremely beautiful result due to Spielman and Teng. So if you combine this with this, you get really an mn time algorithm. And I would encourage people here who are younger to try to come up with such an algorithm for this problem without using any of this. It's not straightforward. So for undirected min cost flow. So which in particular has this transportation problem. So yeah, it's not obvious to come up with an mn time algorithm, and you can do it. Okay. So anyway, I'm not here to sell the running times, but more importantly for me, the fascinating thing is that it can do all this stuff. Okay, so what about directed flows? And obviously this is a typo. So the Physarum can also compute directed min cost flow. Okay. So sorry about this. This is just cut and paste, I believe. So now going to the directed min cost flow instances and running the directed discrete dynamics, we can again come very close to the optimal solution with a worse step size. However, it is still polynomial in the sense we described before. Okay. This also has a slight twist that you need to precondition the graph in the beginning. Which is, I will explain later, it is really just adding a few edges, which can be done in linear time based on the pairwise demands. And then picking a starting point depending upon how you have preconditioned. So it starts getting hairy and hairy, all this analysis, once you, and I don't claim at all that this is optimal. This is just the first convergence bound. And finally, for people who really care about continuous dynamical systems, we can also prove the missing link in the paper of Ito that there is actually a solution for that continuous dynamical system. And this is yeah, so this implies that even the continuous dynamics converge. Okay, so so in summary, we improve and generalize and give stronger results on the computing powers of this Physarum organism. Okay, so any questions before I go on to giving some proofs?
So in your third point, it converges to the optimal solution?
Yeah, it converges to the unique optimal solution, yeah. So the proofs, as we will see, combine several things. It's quite elementary, I would say. I mean, nothing really fancy math, but still combines things like electrical flows, combinatorial flows, some barrier functions which are reminiscent of interior point methods, and the kind of update analysis which is reminiscent of the multiplicative weight update method. So it's a nice elementary connection of ideas which allows us to get these results. So for the rest of the talk, I will sketch a proof largely for the undirected case. The directed case becomes quite a bit more complicated. I'll tell you a little bit about it, and then if I have time, I'll show you a slide on the continuous dynamics. Okay, so let's start with some basics. So we are back to the undirected discrete dynamics. Recall that we have a dynamical system where these conductances are evolving by looking at the past conductances and adding them this magnitude of the flow. So it's really a convex combination of these two quantities. Okay. So here, for instance, you should not be surprised that if you start with a positive solution, you'll always be positive. But let's see. So we need to do a little bit of setup. So let's say f star is the unique optimal solution, and the graph is undirected, but let's choose a incidence matrix corresponding to some assigning directions to these edges, so that this flow is positive with respect to this matrix. Okay, so that we don't have to keep putting these absolute value. Now some basic stuff from electrical networks. So for every k, we consider conductances which are opposite, inverse of resistances. These are really, this is really a diagonal matrix, an m cross m diagonal matrix, which for every edge associates a conductance xck by the cost. So once you have this yeah, I think this should be B transpose WB. So this is the graph Laplacian, which is nothing but B transpose the conductances times B. Okay, I guess everybody here is familiar with this. Once you have a demand for current across each node, you can solve the system of equations and get the voltages at each node. Okay. So this is all standard stuff. So we will use P to denote voltages or potentials. And then we have these currents, which are just obtained by using Ohm's law, by looking at the potential difference across each edge and then multiplying it by the conductance. Okay, so these are the currents. Yeah. And finally, for every electrical flow, there is a natural notion of an energy, which is really the energy dissipated by the electrical circuit. And one can define it to be this quadratic form in the currents. Okay, so this is really just the sum over every edge, current times the potential difference. Okay, so let's quickly check the trivial thing here in the undirected setting, which is that if I start with a positive solution, then I always remain positive. This is easy, right? Why? Because, well, just observe by induction. So you know that this is positive. You're adding something positive, so you can't really become negative. In fact, you're strictly positive. Okay? So here is where all these absolute values help you. another nice thing to, okay, so now we have to understand how do we pick a starting point, and this will be based on the following considerations. So first note that if I have an electrical flow in a graph, then the maximum current flowing through any edge cannot be more than the total demand. Yes, I mean this is a basic fact about electrical flows. So now if we set our initial conductances to this value, this total demand, then we would get that the conductances remain bounded by this for all k. Okay, this is again by just convexity and induction. Okay, so we both have a very nice uniform lower bound and a uniform upper bound. By uniform, I mean that's something that doesn't depend on k. It's easy to get bounds here which start chasing away to infinity or 0 as k is increasing. We really want to be away from these in terms of k. So again, a very simple fact that if I look at any cut in the graph, a cut in a graph is a partition into two vertex sets, S and S complement, and I look at all the edges that go across. I look at, in absolute value, the total flow that goes. It has to be at least the demand of the set S. This can be more, right? Because you're counting positive and negative both as positive. Okay, so everybody's shaking their head, so this is really all straightforward stuff. So again, by induction, this implies that for every k, the sum of these conductances across, and so fix a cut and then look at this quantity. Okay, this is at least Bs. Okay, note that initially, for this to be initially true, there has to be one edge that goes across the cut. The graph is connected. We assume feasibility, right? So there has to be one edge that goes across, and that for that edge you had Bp, which is bigger than Bs. So initially it is true, and then at every step it is true. So this is very nice, okay? Because this allows us to use the Max-Flow-Min-Cut theorem. And it implies that there exists a flow, okay, which again will depend upon k, which is bounded by x's. So let's step back and see, okay, so really what we are trying to prove is that the solution x to this dynamical system converges to a flow. Okay. However, at no intermediate stage, it may be a flow, because it doesn't have to satisfy the flow conditions. What this says is that there is a proxy flow, which you can keep in mind if you want to think of, and this flow is capacitated by this conductance vector x, and we call it the x-capacitated flow. Okay. So our choice of initial vector is such that we have the existence of such flow at any given time. Okay, so this is all like black magic, yeah.
What were the BVs again?
So BVs are demands. So for the shortest path at S you had -1 and T you had +1. Now we are solving a general flow instance.
But demand is a pair.
No, but you could say I want 3 units current here. I want.
Oh, this is current.
Yeah. I mean, in a general min-cost flow problem, you set up your demands. Yeah, which could be a positive or a negative number. We assume that their sum is 0. I mean, only then the Laplacian will have a solution, right? Is that clear? I mean, it's all very simple and very soon. Okay. So now we come to the key question: how do we track progress? Okay, so we need to introduce some ways to track progress. So of course, one thing that we introduced was the energy of a flow. So now for this slide, I will drop the k. It's clear when I talk about this that I'm referring to the kth vector. When I want to talk about differences, I will reintroduce them. So energy is one quantity which one could track off. Unfortunately, this doesn't turn out to be the greatest potential function. Another one is the cost. So since in my mind I'm thinking of the current solution as a flow, it's not really a flow, but I'm thinking of it as a flow. So then I would expect that this quantity here is a reasonable potential function, and that this should go to the optimal value. Right? That's one reasonable assumption, not assumption, but desire, assuming that all this actually works. So let's see that at least it is a reasonable notion. So the notion of excapacitated flows, for instance, allow us to show that indeed that this cost is at least the optimal. Okay, and why is that? So the cost is defined to be the sum of these conductances, weighted conductances. Because each of these flows are bounded by xc's, this is an inequality which you get from the definition of the excapacitated flow. And now this is a real flow, so this cost cannot be more than the optimum. So you see it's a lower bound to the cost. Another nice thing that you can prove is that the energy is also a lower bound to the cost. And this again follows from a very simple fact from electrical networks, that a flow which minimizes energy is the electrical flow. So let's look at this simple chain. So this is a flow. This is the optimal flow. So this energy is less than this. But this is capacitated by x. So this is just, okay? So we have some nice relations. And it is really not too difficult to show using a Cauchy-Shor's that the change in cost is really something like energy minus the cost. Okay? And by what we just observed, it's non-negative. So at least you don't expect this cost to increase. So it may not be, so it's possible that this actually might work. Okay? And this is really, yeah, so if this number is negative, this is negative. Okay, so this approximation is written to hide some terms, but that is true. If energy is less than the cost, then the cost decreases. So we would be very happy if this number was going down, okay, at an iteration. This would be a happy iteration for us. But we also have to take care of or rule out that energy cannot become close to cost. If this really starts becoming the same, then we are getting, then this potential function is not really changing. So how do we do that? Okay, so here is where comes this idea of using a barrier function. So we use the following function, okay, which is, so you pick, let's say f star was the optimal flow. Okay, and for every time step k, you define this following function. Now what it does, and why I call it the barrier function, is that as x's approach 0, this number goes to minus infinity. Right, so it's really a barrier for this positive orthant. Okay, and you will see why I put in the f star there very, very, very soon. But this function will be very important for us. So let's try to understand, and this is really the most technical slide, so bear with me. But this is more or less where the proof will end also. So if I now try to understand how this barrier changes, this is an equality which just follows by the fact that log of a minus log of b is log of a by b. Okay, so it's easy. Now I plug in what the formula for xc k plus 1 was. So what was it? Oh, no, there is, yeah, C is missing from there. Yeah, sorry. Yeah, we will see why C is required. Okay, yeah. Thanks for pointing that out. Yeah, and so we now look at what this ratio is. Remember that xck plus 1 was just a convex combination of xck and qe with respect to h. So this is really what it is. Okay, so you have log of 1 plus h times some quantity. Now let's just rewrite this quantity in terms of, so this is the current, And we know that the current is nothing but the potential difference times the conductance. So we get this here. Okay, with delta sub E of P denotes the potential difference across an edge at time k. Now we all know what to do now, right? We want to kind of get rid of the log. The log has done its job. So we need to open this. And we can open this when, or we can approximate it by linear function when this quantity here is small. Okay, so that's exactly what we will hope for. That assuming that this quantity here is very small, we can approximate this by that. Now let's just plug it in. Now everything will linearize nicely, and you'll see the C was required. Okay. So now again, let's go back to this formula here: barrier k plus 1 minus barrier k. And what we have really done is replaced this log term by that h times the potential difference by cos minus 1, and we have split these two terms. So the f star CE term will give you 1 opt. That gets multiplied with h. So this is h opt. What about this term here? So this cost and this cost gets cancelled, right? And this is this is really now just the inner product between the flow vector times the incidence matrix applied to the potentials. Why? Because the incidence matrix does exactly this. It gives you for every coordinate the potential difference. Now notice here that I have dropped the absolute value. Okay, so it's fine, because if you want to do it correctly, it's fine. We are only interested in a lower bound in this. And now magic happens, right? So I know that, so I've used the optimality of f to get this opt here. Now I will use the feasibility of f star to get a b here. I know that f star is a flow. So bf star is equal to b, or b transpose f star is equal to b. Yeah? But b transpose p is really just the energy of this flow. Why is that? Yeah, this is the definition. Yeah. So good. So we get something very clean, that this bk plus 1 minus bk is at least h times the energy minus opt. So this is really good. Whenever energy is much bigger than opt, this barrier increases. So now we have found another potential function through this barrier, which increases. So we could take the negative of this if you want something that decreases. And now we can just combine the two scenarios. So remember that we have to run our dynamics up till the point where the cost is bigger than the opt. Now for this to happen, either this must happen or that must happen, just by triangle inequality. And in either case, you win. Okay, you can make all this very quantitative and correct, and you get the result. So what is left to prove? We assume something about, we assume that this is, so we are really not done, because this is saying now that these potential differences in these dynamics should not run off to infinity. This can happen. I mean, unless you rule it out, this can very well happen. Okay, so now the task reduces to bounding these potential differences. So that we need some effective bound on H, because if you can give me some bound on these potential differences, then I can pick H to be 1 over that bound. Okay. So how big can these be? Any guess? Okay, let's see. So I claim that the maximum potential difference across any pair of vertices can be at most n times the largest cost. Okay. Now for here, if you go back to shortest path, the proof almost is immediate, because in a shortest path setting, you know that the maximum and the minimum potential is at the source and the sink. and you can bound that by m. So you can easily recover the m bound from this. In fact, you can even recover something better. So let's see a proof of this. Okay, again, very simple. So it's useful to now lay down the vertices on a line, okay, based on their potential. So this is lower potential, that is higher potential. The left is lower potential. I've just sorted all the vertices. And let's say you claim that this is not true. So there will be some pair where this is, okay, so this is what I will prove actually. So I will prove that for every neighboring pair in this ordering, I can bound the potential difference by C. Okay, and that implies that because the number of terms is at most n times. So assume that is false. So assume that there is a neighboring pair U and V where the potential difference is actually quite large, bigger than C. Now let's look at this cut between these, which keeps U on one side and V on another side. Okay. So we know that the electrical flow, since it goes from higher potential to lower potentials, the total flow shipped by it is equal to Bs. Okay. So everything on the right, remember, is positive. More than everything on the left. So nothing is going backwards here. So this is really, the sign is not important here. So we have that this quantity here is equal to Bs. But what is this quantity? Let's rewrite it. So this is current. So current is potential times conductance. Okay. But now I have assumed that the potential across this particular pair is at least C, bigger than C, and in particular every edge that goes across the cut must have more than C potential difference. So what I get is that this is strictly bigger than XE times C by CE. But C was chosen to be the maximum of the costs. So you get that this is at least XE. But if you recall one of our, from this notion of excapacitated flow or just from induction, we had that this quantity is at least Bs. So we get that Bs is bigger than Bs, which is just Bs. So we complete the proof. Okay? And it suffices now to just pick H to be 1 over NC, and that's really the end of the proof. Okay, so as you see, it's really elementary. It just puts together some facts from flows, combinatorial and electrical.
Where did you use uniquity?
Where did I use unique? So actually, I did not. And the theorem says, if you go back and look at the theorem says that the xk times the cost converges to the optimal value in these many iterations. So really, this is what will happen, that you have this plane, which is the equi-cost surface, and it will go and really close to that. Now from there on to move to a real flow, it can take a lot of time. So in this argument, I did not. You could have chosen f star to be any optimal flow. I did not use the fact that f star is a unique optimal flow.
So generally you have a problem with rounding?
Sorry?
If there are many flows and you will get a fractional flow and you won't be able to round it?
I mean, no. I mean, it depends what your interest is. If you really want the flow, then you need to pick epsilon to be really small. Okay, because then that's one way for you to control. On the other hand, if there are really all these flows are the same, yeah, you could, and you don't really care. You could use the isolation lemma to start with. So the Mulmule-Vazirani isolation lemma, you perturb the cost a little bit so that it's guaranteed that this flow is unique. Yeah. Okay, so what happens in the directed world? So here actually things get quite complicated, and I'm just going to give.
Corresponding natural system that corresponds.
Sorry?
Does this correspond to some natural setting, directed?
That's a good question. It's, yeah, for the Physarum dynamics that I showed in the earlier part of the talk, that is not directed. But this was proposed by some people who were looking at this.
Yeah.
I think you missed part of the.
Yeah, but what I'm saying is.
Yeah. No, it's not. So that's why I use the word nature inspired.
Okay.
Yeah, I don't say this is, yeah. But who is to say that one will not discover such a dynamical system, right? So we don't know that that doesn't exist either. But anyway, we are mathematicians, so we like to solve math problems. So what is, again, let me recall that here we drop the sign and we go back to this notion of dynamics. So now I'll tell you what the preconditioning does. Okay, it looks at pairs of vertices where there is an edge going from one to the other, but the starting point of the node of the edge has a negative demand, and the ending point has a positive demand. Okay, and to this edge, so we add each. So if there was no edge present between these two guys, or even if there was, I will still add an edge between them, and give it this cost. It's very high cost. Okay, and this is why things kind of look more screwed up in the expressions where I wrote down the directed flow theorems. So now I just give you what are the things that one needs to do. Okay, so now proving positivity is not straightforward. So however, we can do it by relating three quantities, which we all looked at in the undirected case. So the first thing we could show is that suppose you assume that starting from x0, x1 till xk, these are all positive, then this implies that in the kth iteration there is a capacitated flow. Okay? Then if there is a capacitated flow, it implies bounded voltages at time k. Okay? And this is, yeah, these are each a couple of page each proof, so I'm not going to go into this. And bounded voltages in turn allow us to prove positivity at time k plus 1, and you can keep doing this again and again. This is your induction setup. And in case you're wondering what is the initial solution, for all the edges it's 1, and for these edges that you added, it's 2m times the product of these demands. So what is nice about this this flow, or this vector x, is that it is really not quite a flow, but it is quite close to being a flow in the following sense. So if you just unravel this by these equations, discrete equations, and you write it down, you will get something like this, that at the kth iteration, this xk is, I think there is a x0 missing here, so it's some number times x0, which is the initial value, and this quantity times a quantity which I call q bar. Okay, so notice that as k is becoming larger and larger, this part is disappearing, and this is what it remains. Now what this is, and I'm not going to write it down, is some geometric average of electrical flows where you give more weightage to the later flows and less weightage to the things that you have seen in the past. So for people familiar with things like multiplicative weight and so on, there we give equal weightage to all the things that we have seen. So here we are giving a geometrically decreasing weightage to different flows, and these are all flows which you have computed. Q's so this is an average over all the electrical flows that we have computed over time.
What do you call geometry? Yeah.
So it's something like you can define something like 1 minus h to the I times qi, and then you look at the sum.
Oh, that geometry.
So it's
Yeah.
a way to just
Yes, yeah, that geometric, yes. So yeah, so okay, so this is not quite a flow. This is a flow, but this is not quite positive. However, you can show that, you know, because this guy is really moving very quickly towards this can be rounded to a flow. If you can show that the flow that you round it to is optimal. Okay.
Does that mean that you're modifying the dynamical system? Or
In the beginning, we modified the dynamical system. But
I understand that.
yeah.
After that, you don't.
No, after that we don't. Yeah. So this is just I will do what.
Rounding, I don't quite understand how that.
Oh, so that's just for proof. Okay. So I want to show that this is converging somewhere. So in my mind, I show that I can round it to a special kind of flow which doesn't have circulations. Okay, a circulation in a flow is something which is, yeah. So, but then I have to argue that it is not, it is an optimal flow. So I have to rule out every other non-optimal flow. Okay, and this is again done by using barrier functions. So for a flow which is not optimal but a vertex in the flow polytope, which is called a basic flow, one can look at the following barrier function. And this can be shown to go to minus infinity as x is increasing. So none of this. So what do I mean? That if there is any xc which has for which g is positive, and then xc goes to 0, because this is going to minus infinity. So that tells you that you cannot be supported on these non-optimal basic flows. Okay, so this is all I'm going to tell you about this directed setting. I'm happy to say more details offline. And this, again, the use of this barrier function. Now this is a specific barrier for each of these non-optimal basic flows. Allows us to infer that the flow that we must have rounded to is an optimal solution. Okay, so Ron, how much time do I have? Okay, so I'll probably just take 5 more minutes and just give you what happens in the continuous dynamics, because it may be interesting to some people. So recall that in the continuous case, you have the following setup where you have dxc by dt is qe minus xc. Okay, and you have some initial point. So by general theory of dynamical systems, I mean, given these functions are all smooth, you're only guaranteed a solution in a very small neighborhood around 0, right? I mean, I should not be preaching to the choir, but I still think that this is important to keep in mind. Whereas we are, for the system to make sense, it has to have a solution for all time. Okay, so how do we extend it? And yeah, using some general purpose results from continuous dynamical systems, we can show that it's sufficient to prove the following: that if I take any time t, which is finite, and for every edge e, if I look at, and so let's say I have a solution up till time t, so I look at a time t for which I have a solution, okay, whatever is guaranteed maybe by this argument, and I look at the infimum of this quantity over this entire interval, open interval on the right hand side. Now if this is positive, then we are fine. Okay, what can happen, and what you have to rule out, is that this doesn't become equal to 0. If this becomes equal to 0, then you are in trouble, which would mean that this t may be the maximal interval for which there is a solution, right? So you need to keep extending. So if you want to keep extending and let t go to infinity, you must rule out this possibility. Okay?
No, I'm confused. It is because you want a solution which is positive.
Yeah. Because negative solutions don't make sense. Yes. Actually, it's another very interesting thing. I mean, for many cases, actually, there are negative solutions, even though there is no physical meaning.
But the fact that things remain bounded, that's no problem.
No, things will always be bounded. I mean, the issue is that they go and touch really close to the the positive orthant. Yeah. So let's assume on the contrary. So let's try to give you a sketch of the proof as how would one prove that. I mean, it's again a very sketchy argument, but give you a feeling. So let's say there is some edge e tilde for which this is really going to 0, okay, for some time. So what this really means analytically is that if I define this barrier function, okay, take any feasible flow and look at this barrier function, if this particular edge E tilde has a positive contribution in this feasible flow, then because this is going to minus infinity, oh sorry, this xc is going to 0, this is going to minus infinity, this derivative, the derivative of this barrier function, right? I mean, this, imagine something remains bounded, but the number is going to, yeah, the derivative also has to go to minus infinity. Okay.
So I think both the function and the derivative.
Yeah, both. But we are interested in the derivative. Yeah. Because we have another way to look at the derivative. So we look at the derivative by taking the derivative of this function. What we get is really, this is just FECE. What we get is the derivative of xc divided by xc. That's what you get when you take a derivative of log. Okay. But we know what xc, dxc by dt is. We can plug in that formula. And what we get is this term minus this term. Okay, now let's just stare at these two terms. So this is some number which has nothing to do with time. Okay? And what is this? This is just the energy of the flow at time t. Okay? And this is always positive, non-negative. And so this is just some, I mean, at most this is some large negative constant. So this cannot go to minus infinity if there is such a feasible flow. Right?
Why would the derivative go to minus infinity?
Because you have a function which remains bounded. We can show that it remains bounded. Okay, so and it is going to minus infinity, so the derivative must go to minus infinity. I think maybe I should add a picture, huh? Finite time, yes. Maybe a picture here would have helped. But okay, so this is this proves to you that for every edge which was in the feasible, which was in the support of this flow, feasible flow, for that this cannot happen. You have to prove this for every edge. And you can do that. I mean, you can extend this again using these sweep cut type argument that I had mentioned. And you can prove this for edges which are not in support as well. Again, it requires you to control the potential difference, which you must show that it is not running away to infinity and so on. Okay, so this is all I wanted to talk about the proofs. In conclusion, we have shown that this Physarum dynamics, both its directed and undirected version, actually apparently can solve flow problems, which is good to know. And the understanding requires, so the proofs require an understanding of combinatorial and electrical flows. And this once again brings to light this interplay between nature and theoretical computer science. And what about what are things to be done? I guess, as I said a couple of times, that these bounds are unlikely to be optimal. So one natural thing to try is to improve them. Second question, which I think is quite interesting, is this preconditioning required? This seems to be just a clever gadget to bypass some technicalities in the analysis. I don't think this is intrinsic. And then finally, and perhaps the most important question for me, is that can we now convert some of these algorithms into really polynomial time algorithms by a better discretization? And thank you for your attention.